Okay, so last week Friday, we were talking about the equations of a line, right? And what we saw is if we have 2 points, we can actually find an equation that describes the line. So what we did, we practiced with the parametric equations, which look like this, right? Parametric equations. So we needed to find x equal x0 plus a, maybe t or lambda, or whatever you want to call it. Y is equal to y0 plus bt, and z is equal to z0 plus ct, right? And this x0, y0, z0, that came from the point. So there's a point on the line, and these are the coordinates of the point on the line. And the ABC was a vector parallel to the line, right? So the way we went about finding it is we said, okay, if we use the triangle law, we could have found a vector, I believe we did O, A, B, right? And we found a vector going in this direction using the parallelogram. So all we had to do to find ABC was subtract the position vectors 4, 4, 4, and 1, 2, 3. Right, so when you subtract that, you get 3, 2, 1, and that was a vector in the direction of the line. So when we substitute our values for A, B, and C, we will get in maybe this as our parametric equation, x0, which is, oh, we could use either point, so let's just use the first point. 1 plus 3t, y is 2 plus 2t, and z is 3 plus t. So these are your parametric equations. You all got that? Nice. And what we said at the end of the class is we could go from parametric equations to something called the vector equation, the generalized vector equation, right? And the way we did that is we sort of had to look at grouping these columns, right? And trying to write it maybe as a column vector. So if we were to write this in vector equation form, we would have x, y, z as a column vector, which is 1, 2, 3, plus, and if I factor out the t, I would get 3, 2, 1, t. Right? So if we write it in vector form or vector equation form, this is our answer. If we write it in parametric form, this is our answer. Everybody okay with that? So I want to go one step further from the parametric form. So instead of going to vector equation form, we'll go to something called Cartesian equation form. Right? And all we are doing when we write in Cartesian equation is we're just removing that scalar, that t. So we want to write each one of these equations in terms of t. So the x equation will become, right, so we had x is 1 plus 3t. So if x is 1 plus 3t, we want to write it in terms of t. So we have x minus 1 is 3t. So x minus 1 divided by 3 is equal to t. Right, and we're going to do that for all the equations. So y is 2 plus 2t. 2 plus 2t. So y minus 2 is 2t. Y minus 2 is over 2 is t. And then the last one is the z equation. Z is equal to 3 plus t. Z minus 3 is equal to t. Yeah. So once we do this, from the parametric equations, we see, well, this is equal to t, this is t, and this is t. So we could actually just equate these three values here, right? So the Cartesian equation form is actually just x minus 1 over 3 is equal to y minus 2 over 2, which is equal to z minus 3. And this is what we want when we say write it in Cartesian equation. Okay, so that's just another direction you could go from the parametric. And of course, if you have the vector equation, you could also go to the Cartesian equation form, right? So you could jump between those three forms, whichever one they ask you for. You all okay with that? And by the way, in the original question, they asked, find the coordinates of the point where the line meets the line z equals 0. So all we need to do, find that, is just substitute when z is 0, right? So we have line that is equal to 0, right? So if we look at, what was, right, z is equal to 3 plus t. So we know z is equal to 3 plus t. But now I'm saying z is 0, so if we substitute that, 0 is 3 plus t. So t is minus 3, right? And then now we could solve for x, y, and z. So if we use x is 1 plus 3t, x is equal to 1 plus 3t. What's the value of t? It's minus 3, right? So this is 1 plus 3 times minus 3, which is just 1 plus minus 9, which is minus 8. And the y coordinate is y is equal to 2 plus 2t. The value of t is minus 3. So now we have 2 minus 6, which is minus 4. So the point where it meets the line z is equal to 0 is just the x value is minus 8, the y value is minus 4, and of course, the z value is 0, right? Minus 8, minus 4, 0. So anytime they ask you something like find the coordinates of a point, all you need to do is substitute whatever they're asking. So if they say at z equals 0, or y equals 0, or x equals 1, it don't have to be 0. You just substitute and solve, and you go down here, right? So that was the solution for that question. Okay, here's another example now. Take a few minutes and try this question. So you don't need to worry about working out the vector equation, the parametric equations. Go straight to the vector equation, right? And just a reminder, we were saying, generally speaking, the vector equation is of the form R is equal to R0 plus U. This is the generalized form of the vector equation. So go ahead and skip the parametric where we break it up into the individual components and just work it as a vector equation, right? So we'll have something like x, y, z is equal to something, 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 plus, And you'll still need to find this vector, I think, t, right? So go ahead and try it like that. Okay, so this one, hopefully it was very straightforward because we did not need to find the parallel vector, right? So what we have, the vector equation of a line is R, so R0 plus U times some scalar t, right? So if we write it in column form, we have x, y, z is equal to x0, y0, z0 plus a, b, c times t, which looks exactly like what we got in the last question, right? So all we need to do is substitute the points that they gave. So r is equal to, what was the point on the plane? It was 137, right? 137 plus, what is the vector parallel to the line? 4i plus 7j plus 15k, right? Now that vector, 4i plus 7j plus 15k. Remember from that first class, what we were talking about, we were saying that the constants, the coefficients, are kind of like our x, y, and z coordinates, right? And the I, j, and k are just our unit vectors to show the general position, right? So the vector itself is actually just 4, 7, 15. Right? You all got that? Cool. And just by the way, if we wanted to write this in Cartesian form, if we want Cartesian form, we could write, well, I'll just say a parametric form real quick. X is x0. Look, our x0 is y0 is here, because this is the point. Look, our a, b, c here, right? So very quickly, x0 would be 1 plus 4t, y would be 3 plus 7t, and the z would be 7 plus 15t. This is parametric equation form, and if we want Cartesian, we just need to solve for t, so we'll get x minus 1 over 4 is equal to y minus 3 over 7, which is equal to z minus 7 over 15. Right, so this is just the alternative forms we could have it. Parametric equation, Cartesian equation. And this is, of course, vector equation. Right. So you all okay with that? Okay. So the big thing we want to talk about today is our next topic, which is the equations of a plane. Right? So just to kind of understand what's going on here. When we are in 2D space, we could have a point, right? This is our x coordinate, this is our y coordinate. We could have a point anywhere in this space. And if we take an infinite number of those points and we extend in both directions, what we actually get is a line, right? So the idea of a plane, if we take infinitely many lines all parallel to each other, we actually form what you call a plane, right? So in 2D space, we have the XY plane. But if we go 3D space, right? So we have X, Y, and Z. We have the XY plane. We have the YZ plane. And we have the XZ plane, right? So this time we have three main planes we working with here. Nice. So what we'll be doing is we'll be taking some of the ideas that we had when we did the equations of a line, and we'll kind of see now, okay, well, if we take infinitely many lines to make a plane, what do we have then? So just like how there were many different equations of the line, the vector equation, parametric equation, blah, blah, blah. There are different forms of the equation of a plane. And what we can do is, based on the information they gave, we can decide how we are going to find the equation in the plane. So the first and easiest way to find the equation of a plane is what you call the point, meaning you get a point on the plane, normal, meaning you get a perpendicular vector on the plane, right? So the point normal equation for a plane is just this. A, x minus x0 plus b, y minus y0 plus c, z minus z0. So this is that is the point normal equation to the plane. And of course, the point has coordinates x0, y0, and z0. And the normal, because it's perpendicular, we'll put a little hat, has coordinates a, b, c. Right? So same idea from when we had the equation of a line. We have a point, we have but it's no longer a parallel vector, nor a perpendicular vector, right? That's just reason, right? So for example, you all try to find the equation of a plane that has the points -3, -2, 4, and perpendicular vector 1, -5, -7. Don't overthink it. Oh no, not -7, +7, sorry. Yeah. Try not to overthink it. Is a nice straightforward substitution, right? So just try that and see what you get as the equation of the plane. Right, so nice and simple. A is 1, x minus x0 is -3, plus b is -5, y minus y0 is -2, plus c is 7 times z minus z0, which is 4. Right, so if we simplify this, we have x plus 3 minus 5 times y plus 2 plus 7 times z minus 4. You all have that? Yeah. So all you needed to do is substitute, right? That is the point normal equation of the line. So we could take that point normal equation now, and we could perform some algebra on it to get a different form of the equation, right? So point normal equation is ax minus x0 plus b y minus y0 plus c z minus z0 equals 0. So if we expand this, we have ax minus ax0 plus by minus by0 plus cz minus cz0 equal 0. You all okay with that? So all I did so far, just expand the brackets. Now I will group ax plus by plus cz and let me write it for minus. Minus ax0 plus by0 plus cz0 equals 0. Right? So all I did, the minus sign outside the bracket will change the sign, right? So I grouped the x, y, z, and then I grouped the x0, y0, z. So let's call this one. Let's call this here D. Just because we know that this is equal to a number, right? Because if we go back to this example here, what I'm doing is I have x plus 3 minus 5y minus 10 plus 7z minus 28. This is my x0, ax0. This is my by0, and this is my cz0. So those values are equal to constants. So I could just call that constant d. That leaves me with ax plus by plus cz minus d is equal to 0. We could just write it as ax plus by plus cz is equal to d. Right? And this is your general equation of a plane. Right? You all okay so far? Right. So we have so far the point normal equation. That might be the easiest way to visualize, right? Because it looks very, very similar to what we did when we had the line equations. So we have our A, or B, or C, or x0, y0, z, right? From the point normal, we could go to the general. We'll look at something interesting with the general equation. Let's look at ax plus by plus cz, right? Remember, ABC is a normal perpendicular to the plane. And XYZ is maybe the general point on the plane, right? So if I write XYZ as R and ABC as N, what you'd actually notice is this AX plus BY plus CZ is the dot product of R and N. Right? Because generally, if I give you X, Y, Z, and I give you A, B, C, and I said find the dot product. It's the first component, product of the first component, plus product of the second, plus third, which is this. So really and truly, we could write the general equation AX plus BY plus CZ equal D. We could write that as a dot product between two vectors, which is also known as the vector equation of a plane. You'll look at that. You'll see where the R and N came from, right? All I did was I took the dot product of the two vectors they gave us. Oh, you'll look at that. Oh, just a side note, right? If we look at where was point out, right? It's kind of the same idea here, right? This is also a dot product. Right? So we have A and the first component of something, B and the second component of something, C and the third component of something. And that something is actually was X, Y, Z, that was R. And what was X0, Y0, Z0? That was R0. You'll see that, right? So another way we could write the vector equation is actually R minus R0 dot product N. That's another way we could write it. And when we write it in this form, it's no longer equal to D, right? It's equal to 0 because look where we took it. We took it from A into X minus X0 plus B into Y minus Y0 plus C into Z minus Z0 is 0. So if we taken it from the point normal equation, then we're going to end up with R minus R0 dot N is equal to 0. If we take it from the general equation, then we'll have R dot N is D. And so they actually mean the same thing. It's just whichever form you might prefer to express it in, or whichever form you might see it in a question. So let's try a quick example. On the plane, I have the points 3, 5, minus 2. And a vector perpendicular is 5i plus j plus 4. I want you to find the point normal equation Then I want you to find the general equation and of course vector equation of this plane. Okay, so take 2 minutes and try this question. Okay, so point normal equation, we need a x minus x0 plus b y minus y0 plus c z minus z. Okay, what are our a, b, and c? A, b, and c come from the vector that is perpendicular to the plane. And this is our vector here, 5, 1, 4. Right? So I'll just write out on the side. A, B, C is 5, 1, 4. And our x naught, y naught, z naught is the point 3, 5 minus 2. C 3, 5 minus 2. Right, so for point normal form, we just need to substitute. We'll get A is 5, x minus 3, plus B is 1, y minus 5, plus C is 4, z minus 2, which is plus 2. Right, so this is the point normal equation. You all got that? Cool. So let's see what the general equation is. And this is a trick. If you all have the point normal form, we could actually just expand it. We'll get 5x minus 15 plus y minus 5 plus 4z plus 8. All right, so all we're doing is expanding the point normal form. 5 times x, 5 times minus 3. 1 times y, 1 times minus 5. 4 times z, 4 times 2. And this will give us 5x plus y plus 4z minus 15 minus 5 plus 8 equal 0. Make sure you have your equal 0 there, right? So carry over everything to the next side. 5x plus y plus 4z equal minus 20 plus 8 is minus 12. Carry over minus 12, we get plus 12. Right? This is in the form ax plus by plus cz equal d, our general equation. You all got this as the general equation? Yeah? Okay, cool. Right. And then the last one, the vector equation. Well, the vector equation is just r dot n equal d. So what was r? R is x. All right, right. Let me write it like this instead. All right. x, y, z dot n, which is ABC, which is 514, 514 is equal to D, which is 12. So this one is R dot N equal D. We could also write X, Y, Z minus, let's see, 0.352, 35 minus 2, 3, 5 minus 2 dot N, which is 514 equals 0. So this one is R minus R0 dot N equals 0. So either vector equation form is fine, right? Whichever one you put in an exam, unless they specify, will be okay. Okay, so we know three different forms for the equation of a plane. We know three different equations for the forms of an equation for a line. Now remember, when we were finding the equation of a line, we could have done it with a point and a vector, or we could have done it with 2 points. So far, we've only been finding the equation of a plane with a point and a vector. So the other way you could find the equation of a plane is with not 2, because it's not a line, with 3 points. So equation of a plane with 3 points on the plane. Right? So generally, we could write that as AP. All right, so that as vectors. So M times AB plus N times AC. Right? So what is AP? Okay, well, A, B, and C are points on the plane. Points on the plane. P is the general point, X, Y, Z. And M and N are real scalars. Right, so M and N, S and T, mu and lambda, and yeah, mu and lambda, all the same thing, right? I just given you all another example now of two different scalars you can use. So you may actually also see this as, if you expand out the vectors, you might see it as X, Y, Z is equal to lambda. Well, let's just put X1, Y1, Z1 plus mu, X2, Y2, Z2. Let's just put that for now, right? Y2, Z2. So this should look a little familiar because this is again one of the general equations of the plane, right? So let's run through a quick example. Example. we have A is 1, 1, 1. B is 5, 0, 0. C is 3, 2. Okay. Oh, and of course, P is the general point on the plane. X, Y, Z. So we need to find the equation that has these 3 points on it. So what I want you all to do first is find step 1, find AB, AC, and AP using vector addition. Right? And just by the way, since these are points on the line, we could turn a point into a line using the position vector, and we could call it OA, which it comes from 0, right? So 0 wouldn't have any additive effect, is 1, 1, 1. OB, 5, 0, 0. OC, 3, 2, 1. These are exactly the same points, right? And OP, well, of course, is XYZ, right? Okay, take a second and use vector addition to try to find AB, AC, AP. Okay, so let's see. AB should be AO plus OB. Of course, if you all wanted to use parallelogram law, nothing wrong with that, right? So that's OB minus OA, which is 5, 0, 0 minus 1, 1. That will give us 4 minus 1 minus 1. Right. AC is AO plus OC, it's OC minus OA, is 3, 2, 1 minus 1, 1, 1, 2, 1, 0. AP is AO plus OP, which is OP minus OA, is XYZ minus 1, 1. Is x minus 1, y minus 1, z minus 1. I'll simplify that. Okay. So we have the 3 vectors AB, AC, AP. By the way, as you all get more comfortable with this, you all will realize if you have to find AB, just take B and subtract A, and you'll get it, right? I keep on writing all these steps for you all to see, but eventually, if I give you all 2 points and I told you all find the vector between them, you should just be able to subtract one time and get it. Okay. Right. So we want to write now AP equal MAB plus NAC. So AP, I feel like it'll be, I'm just gonna write it in column form so you all can see it a little bit more clearly, right? Because I don't want a long, long line going across the page. So, let's put this in column form. So this is just 4 minus 1 minus 1, 2, 1, 0, x minus 1, y minus 1, z. right? I just take it and I put it vertically instead. So we need AP, we need AP is equal to, let's use S. Let's keep it with the form. MAB plus NAC. So this is just substitution now, right? Because we have AP, we have AB, we have AC. So AP, which is x minus 1, y minus 1, z minus 1, is equal to AB, which is 4 minus 1, m, plus AC, which is 210, m. You all okay so far? Okay. So let's try to write this as a system of equation. What does that mean? First things first, let's write it as x minus 1, y minus 1, z minus 1. And let's combine these two vectors here. So we have 4m plus 2n minus m plus n, and then minus m. You'll see what I did there, right? Remember column form and row form. They are analogous to each other, right? So I'm just going 4m plus 2n, that's my first entry. Then I'm going minus m plus n, that's my second entry, right? And it just comes from, right? Going straight across. Okay, once we have this now, we could try to solve for m and n. But what we'll do is we don't want to do constants like when we were solving intersecting lines. What we'll do instead is let's look at this last equation here. Z minus 1 equal minus m, right? So we have z minus 1 equal minus m. So try this in terms of, yeah, m is equal to 1 minus z. So I could write that now in this equation over here. So I have y minus 1 is equal to minus m plus n. But what is minus m? Y minus 1 is z minus 1 plus n. So y minus 1 is z minus 1 plus n. So n is y minus z minus 1 plus 1 is 0. Right? So y minus z. So now I have m and n in terms of y and z. So I could put that in this first equation now. Right? So I have x minus 1 is equal to 4m plus 2n. 4m plus 2n. Right? So x minus 1 is equal to 4. What's our value for m? It's 1 minus z. Plus 2 was our value for n. It's y minus z. And I could expand, I'll get x minus 1 is equal to 4 minus 4z plus 2y minus 2z. And then we can bring over everything on one side. So we have x minus 2y plus 2z is equal to 4 plus 1, which is 5. Right? X minus, I make a mistake somewhere. Yeah. This should be minus 6, no, 6z over here, right? Minus 4z minus 2z is minus 6z. So when we bring it over, it gets plus 6z. Yeah. And this looks very familiar because this is just AX plus BY plus CC equals D, which is our general equation of the plane. So the only difference is we had to work in terms of M and N, which are scalars. And we tried to work with those, and we eventually got, by substitution, the regular equation we are accustomed to. Now, I know I kind of rushed through it a little bit, but the reason I brought this up is because this is actually a pretty kind of long process, right? And it does get confusing when we reach over here and we have to substitute the M and the N values. So what we do is we introduce something called the cross product to help with that. So go ahead, take a second, take that on, and then we'll talk about the cross product. We're going to talk about now cross. You all okay to move on, or you needed to see anything else from the solution? Right. So the cross product we briefly mentioned in the first class, and I said I'd come back to it when we did matrices. But I think if we do it now, it would make a lot of the calculations easier, because what will happen is we'll actually skip this whole M and N step and we'll go straight to the equation. So the cross product of two 3x3 vectors. Let's say we have a vector v1, which is a1i plus b1j plus c1k, and v2, which is a2i plus b2j plus c2k. Then the cross product is the determinant of the 3x3 matrix I, J, K, A1, B1, C1, A2, B2, C2. So I know we didn't really go over anything with matrices as yet, but I'll just give you all the kind of format we're using to calculate this determinant. And when you all see it again in matrices, hopefully you'll remember. So to calculate the determinant, first thing we're going to do, we're going to block out, block out this first row, this first row and this first column. Then we'll take the determinant of the remaining 2x2 matrix. Right, so we're going to have all we do for the determinant here is we multiply the diagonals, right? So B1, C2, and we subtract the other diagonal, C1, B2. Put that in our brackets, we multiply that by I. So a minus sign. Now, we'll block out. I can remove it. This, we're still on the first row, but now we're blocking out the second column, right? So now we need the determinant of the remaining, which is A1, A2, C1, C2. So open bracket, we take the product A1 times C2 minus the other product C1, A2. Right, and we multiply that by the one we blocked, which was J. And the last term, we block out the third row, plus, and we take the product of the remaining matrix, right? So that is A1, B2 minus B1, A2. Right, and we just multiply by what we blocked out, which was K. Right. So without going too much into the theory with the matrices, this is our general form of the cross product. And just by the way, we alternate in signs, right? So we started with a plus sign, then we went to a minus sign, then we went back to a plus sign. That's how you remember where the minus sign goes. Whatever sign you start with, so we start with plus, then you change, then you change. A very quick example. Let's find the cross product between the two vectors. V1 is 3i minus j plus 2k, and V2 is I minus k. All right. So I'll help set you all up really quickly. So to do this, we take the determinant of the 3 by 3, we put the I, the j, and the k, and then our first vector is 3 minus 1, 2, and our second vector is 1. There's no j component, so we put 0, minus 1. Right? So you'll try to find the cross product then. Okay, so if you want the cross product, this is just so we'll block first row and the first column. Oops. Right. And we take in minus 1 times minus 1 minus 2 times 0. I. Nice. Now we block in second column. So we'll change the sign minus 3 times minus 1 minus 2 times 1. J, change the sign plus. Now we block the third column. Yeah. Block the third column. And we take 3 times 0 minus 1 times 1. What is the vector that we get here? Minus 1 times minus 1 is 1. Minus 0. 2 times 0, 0. So I minus 3 times minus 1 is minus 3, minus 2 times 1 is minus 2, j, plus 3 times 0 is 0, minus 1 times 1 is minus 1, so plus 1, right? So the vector is 1 minus 0 is 1, I, of this I, minus 3 minus 2 is minus 5, so that'll change to plus 5j plus k. And this is our cross product. You all got that? Cool. Okay, good. So I will show you why the cross product will help us cut out some of the steps here when we do it this way. But I think, let's see, it's 4:30, so you'll want to take like a 10-minute break and we start back. All right, okay. So yeah, go ahead, take a break and get something to drink or eat or whatever. Okay, so here's why the cross product becomes so important. You see, I think I briefly gave an explanation of this in the first class, but if we have two vectors, let's say v1 goes this way, and maybe v2 goes this way. Then the cross product of v1 and v2 produces a vector that is perpendicular to both of these vectors, right? It'll form 90 degrees here and 90 degrees with v1. So we'll call this n, right? So the cross product gives us a vector perpendicular. So why that is good for us is because we know from when we're doing a point normal equation, if we have a point and a vector perpendicular, then it's very easy to find the equation, right? So if we go back to this example here, where we had 3 points, A, B, and C, instead of doing all these tedious calculations to find M and N and then go back to the plane, what we could do instead is we could say, okay, I have A, B, C. I don't even need to worry about P, right? So let's copy this down. I have A, B, C, and it's very easy for me to find AB, which was 500 minus 111, which is 4 minus 1 minus 1. And it's also easy for me to find AC, right, which was 321 minus 111, which was 210. 210. Next. So what I'm saying is I have this plane, right? In 3D space. I have X, Y, Z, and I have a plane that goes somewhere like this. I have A, B, and C on this plane, 3 points. And what I just did was I found AB and AC, which are two vectors on the plane now. So if I have two vectors on this plane, and I have an operation that gives me a vector that is perpendicular, then what I need to do is find the cross product of AB and AC, and that will give me N. I already have a point on the plane, so I can find my general equation, right? So let's try this. Find the cross product of these two vectors here. Find AB cross AC. Take a second and try that. All right, so if we want to find the cross product, we need this matrix here. So we have I, J, K. Then we have 4, minus 1, minus 1. And we have 2, 1, 0. Right, so first I'll block out that first column and the first row. And what do I have here? I have minus 1 times 0, which is 0. And minus 1 times 1, which is minus 1, I. I switch the sign, so minus. Now I'm going to block out the second column. Right, so I have 4 times 0, that's 0. Minus 2 times minus 1. So I make a mistake somewhere. Minus 1 times 0, minus 1. Oh, yeah, there should be plus, right? Yeah, minus 2 times minus 1, which is minus 2. So that'll also change the plus. J. Switch the sign again. And we shift over to the third column. Right, so I have 4 times 1, which is 4, minus 1 times 2, which is minus 2. That'll change to a plus. K. So my normal vector is I minus 2J plus 6K. Right? And that should look a little bit familiar because when we did it the other way, we ended up with the equation being, I think this was the equation when we did it the other way, right? It was x minus 2y plus 6z equal 5. So look, right off the bat, we know this here is supposed to be A, this is supposed to be B, and this is supposed to be C, which is exactly what we get when we take the cross product. A, B, and C, right? 1 minus 2, 6. Right, so we have a point on the line. Let's just use, we could use the first point, A is 1, 1, 1. So our point normal equation, we have point normal equation, A times x minus x0 plus B times y minus y0 plus C times z minus z0 equals 0. So let's use this vector here that we just found and the point 1, 1, 1. So substitute that and tell me all what you get for the equation. So we're using 1, 1, 1 and we're using 1 minus 2, 6, right? So we have 1 x minus 1 plus minus 2 y minus 1 plus 6 z minus 1 equals 0. So we get x minus 1 minus 2y plus 2 plus 6z minus 6 equals 0. Right? Minus 1 plus 2 is 1. 1 minus 6 is minus 5. We carry that over, we get x minus 2y plus 6z equal 5. Right? So we get the same exact thing we got when we did it the long way. So you can see now why we need the cross product, right? Because this was all the work we had for the cross product versus this whole long, drawn out, confusing thing where we need to find m and n and whatnot, right? And just by the way, I said we could use any point, right? So let's try b as 5, 0, 0. So if we did a x minus x naught plus b y minus y naught plus c z minus z naught plus 0, right? So let's try with b is 5, 0, 0, which was also on the plane. So a is still 1, because this is the normal vector, right? So this doesn't change. Minus 5 plus b is minus 2, y minus 0 plus c is 6, z minus 0 equals 0. X minus 5 minus 2y plus 6z is 0. So when we carry over the 5, we get x minus 2y plus 6z. Hi.
You have a class of 6.
Yeah.
Right. You only have class to speak and so.
Yeah, for sure.
Right. Yeah. No, this is for
Yeah, yeah. Our class was originally parametric.
Right. Yeah.
But when I think the AC now within there.
Right.
So I talked to Dr. Rahman and I asked him if he could come.
Right. But the book this is my class for him for next 3 hours.
Oh.
So I'm gonna try to go downstairs to the 114 and see this week.
Okay.
So I'm trying to go downstairs.
Yeah, well then we'll just have to move on.
Yeah.
That's fine. But you sure we can probably just move one time enough because I'm finishing up this example. Because if you're scheduled to be there. Only so. Because Monday was the same issue, but they had linear 1 in here and they said they're not offering it, which is why I asked Dr. Rahman if we could just come over here instead. But so I don't know if he thought I only meant.
Yeah, I'll go downstairs to 114.
Okay. I think he thought I only meant on Mondays. Okay. And go. Okay. And from next week, what you want to do? Come back. Ah, okay. 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 Where were we? Ah, yeah. Well, 5. Right. So what happened here is regardless of which point we use, if we use A, if we use B, and we could have used C, we get in the same equation of the plane, right? Which is the same thing we got when we did it the other method. So that is why we need this cross product, right? Because it's going to save us a lot of time. So in general, if we have 3 points on a plane, or we have 2 vectors on a plane, take the cross product, we find a normal vector, and we go through with that. Right? So that is the equation of a plane with 3 points. Okay, so just like with lines, after we found the equation of a line, then we went on to find the intersection between 2 lines, right? So now what we want to do is find the intersection between 2 planes. Two planes. So in 2D space, oh, it could be in 3D space too, but let me just show you the two lines here. When we have two lines intersecting, what happens? We have a line going here, maybe we have a line going here, right? These two lines meet at a point, and this is called the point of intersection, right? And that's because lines are made up of an infinite number of points. So think of points like the building block for lines. When we have two planes, it's the same concept, right? Because a plane is made up of an infinite number of lines. So when we intersect two planes, we're going to try to draw this, we get a point of, we don't get a point of intersection, we get a line of intersection. So I know that's kind of hard to see, so let me see if I could steal something. Right. Okay, so if we intersect two planes, you could clearly see here, they meet at a line, right? So there's no point of intersection of two planes. We have a line of intersection instead. But it's very similar to what we were doing when we were finding the intersection between two lines. All right, so let's go back now. So let's say we have two planes. By the way, we called the two lines L1 and L2, right? Alpha line. We don't call the planes P1 and P2 typically because P is usually points. So we call the planes something like pi1 and pi2, right? So let's see. We have the planes 3x minus 5y, 3x minus 5y plus z equal 8, and 2x minus 3y plus z equal 3. I'll just call this 1 and 2, right? Okay. So what we want to do, we want to try to do this kind of simultaneously, right? It's just when we solve it, we're not going to get a point, we're going to get a line equation. So if we subtract 2 from 1, we could get rid of z. And that'll be a little bit easier for us to work, right? So we subtract, so we have minus 2x plus 3y minus z minus 3, right? Because the minus will change the sign here. So we get 3x minus 2x is x, minus 5y plus 3y is minus 2y, and z minus z is 0. 8 minus 3 is 5. So we have this third equation here. And what I want to do is I want to write x in terms of y. So therefore, x is 5 plus 2y. Now, if we want to find the equation of a line, we need to do something. We kind of need to put a placeholder to see how the other variables are related to each other, right? So what I mean by that is, remember that scalar we were using to find the equation of a line, like s or t or lambda or mu? We're going to use that here. So just for now, instead of solving a value of y, we're just going to let y equal mu, or t or s or whatever you want to put, right? And the reason we're doing this is because we don't have another equation to solve x and y simultaneously. So we kind of just need to put a placeholder for y and see if we can solve x. So now x is 5 plus 2 lambda. Oh yeah, y is equal to lambda, right? So we have x is 5 plus 2 lambda and we have y is lambda. So now think about lambda as a scalar. We kind of have numerical values for x and y now, right? So this is exactly how we would have solved it before. It's just instead of a constant like a 3 or a 2 or a minus something, we just have lambda. So we're going to sub. So let's put x and y into equation 1. So remember, equation 1 now is the equation A plane, right? So we have 3x minus 5y. So 3x minus 5y plus z equal 8 plus z equal 8. You could just substitute directly, right? But the 3x is 5 plus 2 lambda minus 5 times y is lambda plus z is equal to 8. So what we could do now is we could expand. We could say, all right, well, that's 15 plus 6 lambda minus 5 lambda plus z is equal to 8. So z is equal to 8 minus 15. 6 lambda minus 5 lambda is just lambda. We bring it over as minus lambda. If you all need to write out the steps, nothing wrong with that. Which is equal to minus 7 minus lambda. You all okay so far, right? So look at this. Now we have x in terms of lambda, 5 plus 2 lambda. We have y in terms of lambda. And we have z in terms of lambda. Does this look familiar? Maybe if I write 0 plus lambda. These are the parametric equations. Parametric equations of a line, right? This is x is equal to x0 plus a lambda, y0 plus b lambda, and z0 plus c lambda. So now we have the parametric equations of a line, and we know that is exactly what we're solving for, because when we intersect two planes, we get a line. Well, this is the line. So we can just write this in vector form. We have x, y, z is equal to 5, 0, minus 7, 7, plus 2, 1, minus 1, lambda. Plus lambda is a real number. And that's the answer. That's the equation of the line of intersection, right? Because the question was, find the line of intersection between these two planes. Well, this is the line. So I know it might be a little tricky at first letting y equal lambda, but the reason we do that is because ideally we would have a numerical value to substitute, but we don't. So we put a placeholder, which is lambda instead. And then we write everything in terms of lambda, and then we get the parametric equation, right? So that is the line of intersection between two planes. By the way, if two planes are parallel, let's say we had phi 1, phi 2, and phi 1 is 2x minus 3y plus 4z, 2x minus 3y plus 4z equal 0. And pi 2 is 4x minus 6y plus 8z equals 0. Could we determine if those two lines are, if those two planes are parallel? Remember when we did lines, we said they're parallel if the direction vectors are scalar multiples of each other, right? So let's check. What is this is the terminology over here is the perpendicular or the unit vector, right? What are the vectors? This is A, B, C. Well, A1, B1, C1. This is A2, B2, C2. Right, so we have 2 minus 3, 4. Is this equal to something times 4 minus 6, 8? Well, yeah, right? If we multiply by 2, we'll get up. If we multiply by 2, we get that. So what we just showed is that, therefore, oh no, since, or hence, or something. Hence, V1 is equal to KV2. Therefore, planes are parallel. So just look out for that, right? Like a 1-mark question could be, why are these planes parallel? Well, the unit vectors are scalar multiples of each other. Could we have skewed planes? Not in 3D space, right? Because remember the whole explanation with lines and this thing that in 2D space lines intersect or they're parallel, but in 3D space they could be skewed. In 3D space, because we have 3 coordinates, the planes cannot be skewed. The planes could only be skewed in 4D space, but we're not dealing with that in this course, right? So for all intents and purposes, when we use our 3D space, no skewed planes, only skewed lines. Okay. We only have 2 more things to talk about for planes. And the first thing is, oh, only 1 more thing to talk about. Right? So the last thing for today, we will talk about the distance between planes. Distance between planes. Right. So let's say we had 2 planes in 3D space, right? So we have this. X, Y, and Z. We have a plane here, and we have a plane here. If we have 2 points on these planes, and these have to be parallel planes, by the way, right? Because if the planes intersect, well, then you're just going to have the same line, which is just a distance as 0. They'll be touching. So these only works for parallel planes, right? So maybe I should say distance between parallel planes. Parallel. Right? That way there's no intersection. So the distance is really the perpendicular distance between these 2 points. And the perpendicular distance or magnitude is something that we saw when we were dealing, right? So let's first of all, let's see if before we could do the distance between parallel planes, let's see if we could do the distance from a point to a plane, right? So let's say distance from a point to a plane. So we have a point. P is x0, y0, z0. What else do we need? We need the plane. The equation of the plane is ax plus by plus cz is equal to d. So we have a plane, we have a point. Then the distance, the perpendicular distance, by the way, between the point and the plane is given by capital D is equal to the modulus of ax0, no, not x0, sorry. Oh yeah, x0 plus by0 plus cz0 plus d over the square root of a squared plus b squared plus c squared. This is a general formula you all will have to know. Right? So let's try an example. Using this formula, find the distance between the plane x minus 2y plus 2z, x minus 2y plus 2z equals 7, and the point P, oh, this is minus 7. Minus 7, and the point 4 minus 3, 5. 4 minus 3, 5. Right, take a second, try this example. Just substitute into the formula and see what you get. And just by the way, this sign here, this is your absolute value, right? So meaning positive. So just side note, the modulus over here, absolute value of x is x if x is greater than or equal to 0, and minus x if x is less than 0. You all have seen that before, right? So all that means, if you get a negative number here, just drop the minus sign. If you get a positive number, okay, great. Keep it, right? So try that. Right, so what is the distance? D is equal to absolute value A x. Oh, right. A, what is x0? X0 is 4. Because of course we know we have A, B, C here. This is D. And this is x0, y0, z0. Right? So A times 4 is really 1 times 4 plus B, which is minus 2, times Y, which is minus 3, plus C, which is 2, times Z0, which is 5, plus D is minus 7, so minus 7. All divided by the square root of A squared, which is 1 squared, plus B squared, which is minus 2 squared, plus Z squared, which is C squared, which is 2 squared, right? So let's see what we get. 1 times 4 is 4, plus 6 plus 10 is 20, minus 7 is 13, divided by the square root of 1 plus 4 is 5, plus 4 is 9. Yeah, so we get 13 over 3, which is 4 and 1/3. You all got that? Okay, cool. Yeah, so for that distance thing, it's just to substitute the value. Where it gets interesting now is we want to find the distance between two planes, right? So let's now try pi 1, pi 2. Pi 1 is x minus 2y plus 2 is equal to 3. And pi 2 is 2x minus 4y plus 4z. 2x minus 4y plus 4z equal 7. Can we find the perpendicular distance between these two planes? Well, first things first, we can only find the perpendicular distance if these planes are parallel. So, step 1, check if planes are parallel. Once they are not parallel, then what we need is to find a point on one of the planes, because as I was saying earlier, we could just take a point on the plane and find the distance that way. So let's take step 2, find a point on pi 1. And step 3, find the distance using the formula for d. Right? So take a second and try to do that. And just side note, if we want to find a point on a plane, all we need to do, what is the easiest point to find? On pi 1, we take y equals z equals 0, and we substitute that. Then x, just 3. So the point on this plane is 3, 0, 0. That's a point on the plane. You can do that with any numbers you want, and you can find any number of points on the plane, right? But I just chose y and z is 0 because I think that's the easiest point to find on the plane. So anytime you need to find a point on a plane or a point on the line, just substitute random numbers, right? So try that and see what you get. Okay, so first things first, we need to see the planes are parallel. How do we do that? Well, we need to look at these vectors here. We need 1 minus 2, 2, 2 minus 4, 4. Are those two vectors parallel? Well, 1 minus 2, 2 is equal to, could we get this by multiplying by a scalar? And the answer is yes, we could just multiply by 2. So since V1 equal K V2, this implies the planes are parallel. You all had that, right? Parallel planes, great. So once the planes are parallel, now we just need to find a point on pi 1. Right, well, of course, we can find a point on any one of the planes, right? So pi 1, let's use this point we found earlier, 3, 0, 0. Then we can substitute into the formula d is equal to absolute value of a x0 plus b y0 plus c z0 plus d all over the square root of a squared plus b squared plus c squared. So if we use any point on pi 1, then we need to use the equation of pi 2, right? So we have the point 3, 0, 0, and the equation 2x minus 4y plus 4z is equal to 7. So if we substitute this, we get absolute value of a, which is 2, times x0, which is 3, plus b, which is minus 4, times y0, which is 0, plus c, which is 4 times 0. D is, of course, 7. Square root a squared, which is 2 squared plus minus 4 squared plus 4 squared, which will give us 2 times 3 is 6, plus 7 is 13. And then 2 squared is 4 plus 16 plus 16 is 36. Square root of 36 is 6, 13 over 6. Okay. Did you all have that? Something go wrong? D is minus 7, not 7. Yeah. Oh, well, okay. All right. So this is the answer if it was equal to 7. Everybody got this? Cool. Yeah, in the original question, this was minus 7. So, but that's okay. In this question, we get 13 over 6 as our answer. Anybody got 1 over 6? Okay, cool. So let's move on now. Right, so that was the distance between two planes. So just to kind of briefly summarize what we just did. So we want to find the distance between two planes, right? And that is really just the distance between a point on one of the planes and the other plane, which is something we did. We showed how to find the distance between a point and a plane. Now, what if we had two lines that were skewed? Would we be able to find the distance between these lines? Right? Skewed. And the answer is yes, because each one of these lines, because they're skewed, they're non-parallel, they're non-intersecting, will lay on a plane. So we'll have something that looks like this. We have a line. Change. We have a line here, which is skewed to this line here. So what we need to do is find the distance between this point on this line, on that plane, and the line on this plane. Right? So it's going to be the same exact formula with one. First things first, we know we are going to eventually need a point on the plane and the equation of the plane. Right? So the point on the plane is very easy to find. Let's look at this example. Example, we have L1, which is x, y, z equal to 4, 1 minus 5, 4, 1, 5 plus 1, 0, 2 t. We have L2, which is x, y, z is equal to minus 1, minus 1, minus 8, minus 1, minus 8, plus 2, 1, 3. Right. So these are two lines. And of course, we know these two lines lie on two planes. And we really want to find the distance between two planes here. So let's find the point on a plane. Let's use L2 this time, right? So for the point, so this line is contained on pi 2, and this line is contained on pi 1. Two planes, right? For the point on pi 2, all we need is a point that is on L2, right? Because if the line is on the plane and the point is on the line, then the point is on the plane. So the point on pi 2 is, remember by definition, this is the point on pi 2, minus 1, minus 1, minus 8. So that's nice and straightforward to find. So what we need to find is the equation of pi 1, right? And we know we can find the equation of a plane if we have a point on the plane and a vector normal to the plane. So we have a point on pi 1, which is simply this point on L1. Again, if the point is on L1 and L1 is on pi 1, then the point is on pi 1, 4, 1 minus 5. And we just need a vector n. So this is going to be our p. And we need to find a perpendicular vector. Well, we have a parallel vector. Parallel vector comes from here, right? Because this is a vector parallel to the line. So this is a vector parallel to the plane. So we have 1, 0, 2. There's V1, which is parallel to the plane. By the way, if we find the distance between two planes, and they need to be parallel, which means a vector that is parallel to pi 2 is also parallel to pi 1. Y'all follow that? We have two planes. And we have a vector on this plane and a vector on this plane. We know these two planes are parallel, which means these two vectors are also parallel, right? So nice and easy. We just use this one over here, 2, 1, 3, as our V2. 2, 1, 3 for V2. So we have two vectors that are parallel to the plane. Y'all followed what I did there, right? So V1 is easy to see. This is V1 over here. And this is obviously parallel to pi 1 because the line lies on the plane. But what I'm saying is we need the planes to be parallel. So if the planes are parallel and V2 is parallel to pi 2, then V2 is also parallel to pi 1, right? So when you're learning these things off, just remember you could use both of these vectors, right? So to find our n, we just take the cross product of V1 and V2. We do that real fast, so we'll get V1, 0, 2, 2, 3. Right, so we have 0 minus 2, so minus 2i. 3 minus 4 is minus j. And then 1 minus 2i. No, yeah, it's plus j. Right, okay. When you're working this out, you all can, of course, take your time, draw the matrix and stuff, right? But this should be what you get when you find n. So what we have a point on the plane and a vector normal to the plane. So we use our point normal equation, which is A x minus x naught plus B y minus y naught plus C z minus z naught equals 0. What is A? Minus 2. X minus what's the point? Point is 4, 1 minus 5, so minus 4. Plus B, which is 1. Y minus 1. Plus C, which is 1. Z minus 5, that'll change to plus 5 equals 0. So the equation in the plane is minus 2x plus y plus z minus 8 minus 1 is plus 8 minus 1 is 7 plus 5 is 12, so it will go over as minus 12. And that is the equation of phi y. Minus 2x plus y plus z equal minus 12. Right? So we want to write in the form ax plus by plus cz plus d. So, oh, well, I guess I could have just keep the, so minus 2x plus y plus z plus 12. This is our equation, right? Square root a squared plus b squared plus c squared, because we want the distance. So a is minus 2. What is x? X is our point on P2. And so now we use this, right? Minus 1 plus 1 times minus 1 plus 1 times minus 8 plus 12. Right? That just came from the equation. The square root of a squared, which is minus 2 squared plus 1 squared plus 1 squared. Right? So this will give us 2 minus 1 minus 8. So 2 minus 1 is 1. Minus 8 is minus 7 plus 12 is 5. 4 plus 1 is 5 plus 1 is 6 is square root of 6. And this is our distance of the plane. Now I know I kind of start rushing, but that's because we're out of time for today. So of course next class we can go over example and so on. But the important thing is just kind of take down the notes on how we find. So to summarize, to find the distance between two skewed lines, we need a point on one plane and equation on one plane. Our point comes directly from the equation of the line, and so does the equation of the plane, right? Because we just take two parallel vectors. We cross them, we get the equation of the plane, and we substitute in our formula. Also, I just realized the reason this was looking weird is because the general form, we want the form in this like this. We want it as ax plus by plus cz plus d, right? So that is 2x minus 4y plus 4z minus 7 equals 0. Right? That's why I was confused for a second. So this should really be minus 7. So you're supposed to get 1 over 6, not 13 over 6, right? So again, we also time for today, so I will go back over these things on Friday's class for any of you who kind of confused, but just go back in the notes and make sure you change that to minus 7. Okay, so in general, that's what we needed to cover for the equations of a plane, right? So on Friday, we'll revise that and we'll do the next topic, okay? Any question? Cool. That's it for today. Okay.